All right, to advanced calc, we're going to work on section 5.4 of the ice sheet. If you look, I put way too many problems on the ice sheet, but in class we went over question 3. We did pretty quickly and used a lot of facts to hit those hard. And question 5, I did in class. I cheated a little compared to the back, and I used the fact that we technically don't know yet that if you have a bounded derivative, then you're uniformly continuous. We're going to prove that in chapter 6. But I don't mind using that. If you want to use that on this homework, you can. Okay, so the next are 7, 8, 9, and 10, and I'm going to skip 15. So 7, 8, 9, and 10 are all about whether tweaking things a bit keeps you uniformly continuous. So we're going to have 2 proofs and then 2 just some counterexample stuff. So 7, I'm hoping you have the textbook in front of you. I'm not going to write these out. 7 says if you have a function from D to R, it's uniformly continuous on D, and then you have some real constant, and I want to take the function K times F and show that's uniformly continuous. So this is a classic trick where you have one limit or one continuity or one derivative and you're trying to show another. So because F is UC, you can say that given, so we're going to say let epsilon greater than 0 be given. And then because F is UC, then there already exists a delta such that x minus y less than delta implies f of x minus f of y is less than something. And we're going to fill that in a minute to be the thing we want. It's probably going to be some variant of epsilon. So if I had like epsilon over 2, that would be fine because f is uniformly continuous. So it works for any epsilon, even some variation of not the epsilon we're looking at, but some different one. Okay, well, our expression, if we want to use this delta in this situation, I just need to think about, that's not necessarily true. Sometimes use a different delta, but here I think it works fine. If you think about k f of x minus k f of y, well, and I want that less than epsilon is my goal. Well, if you pull the k out like that, then you would have the stuff above. Sorry, I'm running out of space here. Then this, going back to this spot, it should just be epsilon over epsilon value of k. That's a positive constant. If my stuff is less than that, everything will work. Okay, I got kind of cornered here at the bottom, but let me do this now from the beginning and try to write out somewhat carefully. All right. Let's go to the next page. Okay, to start from the beginning, we're going to say let epsilon greater than 0 be given, and then there exists delta such that x minus y less than delta implies that f of x minus f of y, because f is uniformly continuous, is less than, we're going to do epsilon over epsilon value k. K is already defined in the problem. And now we're trying to talk about kf, so let's use the same delta. So that's what we're going to be using. So then I want kf of x minus kf of y. That's my new function. Now I'm going to do a little bit of algebra. K out of the absolute value, but it stays in absolute value. I factored it out, basically. And now that stuff, I did this backwards. That stuff on the right becomes less than epsilon over epsilon value k, but I also had the one on the outside, and so that becomes epsilon. So there's a lot of words I should be writing in between, but that's the general way that's going to look when you're done. Okay, so that's number 7. Let's go ahead and go to number 8. Okay, so number 8 says you have f and g are real value functions that are uniformly continuous on a domain D, and the g of x is not equal to 0 for any x. And it says find an example that the quotient function still need not be uniformly continuous. So just think, for several of these counterexample problems, don't make it harder than it is. First, just think of a function that's not uniformly continuous. So if you think about, and we're thinking about division, so think about a fraction. This guy here we talked about in class has vertical asymptotes aren't going to work for this. So if you do this like on 0, 1, it looks like that. That's not uniformly continuous. So your functions then would be constants are uniformly continuous and so are lines. So those are the 2 functions, f and g. And then Part B says prove that it works if D is compact.